Hello everybody. Today we're going to be talking about soil physical properties, so let's get into it. So first up in terms of our soil physical properties is soil texture. So when we're talking about soil texture, how would we define soil texture? We would define it as the relative portion of the grain size. So what does that mean? Well, you're going to have different sized grains that are going to mix together in the soil, and each of those each piece of soil is some sort of a mixture of sand, silt, and clay. Those are going to be our main ones. There's also some people throw in gravel, which is just, the much bigger. Gravel is basically little rock fragments, and then sand and silt are even smaller broken fragments of broken down rock fragments. Within the sand and silt, you're going to have minerals like quartz, feldspar, mica, and other materials. And sand and silt are extremely important as the skeleton of the soil. They're really they're there to give it structure, and really helps to provide structure to where we're going to also get that pore space for the air and water. But sand and silt are going to provide us some structure in the soil. Silt is also really good at holding water in the soil, and not only just holding water, but water that's available for plants, and that's a big deal. We'll talk about water a lot later on in this class, but there's water in the soil, and then there's the water that's available for the plants, and silt is really good at holding water that's available for the plants. Clay, and why would you want clay? Clay is really good at holding water, so that's one reason, but also clay is highly absorptive of water, gas, and dissolved nutrients. Dissolved nutrients, we're also thinking minerals, so we're silicon, aluminum, iron, magnesium, all those minerals or nutrients, whichever way you want to look at it. Clay is plastic and sticky. When wet, I always kind of describe it as Play-Doh. It's a negatively charged colloid, and a colloid just being a combination of things that are it's just a compound that's basically full of stuff that's too small to see. In the most simplest terms of a colloid. So don't get confused on terminology like that. It's just a term that means it's a grouping of things that are too small to see. But it's negatively charged. That's the important part. And why is that the important part? Because it's going to then attract positively charged cations, and then we're going to have cation exchange happening between the plant roots and the soil water, and that's going to be important later on when we discuss that in much greater detail. So let's take some looks here. So with our soil texture, sand are the only particles that we can actually see, and if you're not sure of that, then just go to the beach, because the beach is covered in sand, and you can pick it up and you can see it, and you can kind of see what size those particles are. Sandy soil has a gritty feel to it. Just think of the idea that something that's really gritty is sandpaper, and it's that grittiness. You can actually feel that grittiness if you pick up some sand, put it in between your fingers. You can feel that gritty feeling, like like something's irritating your skin. Silt are smaller than sand particles. Silty soils, or soils that have a high silt component, are going to feel powdery. What does powdery feel like? Think about flour, like baking flour, all-purpose flour. That sort of feeling, that's what silt, a soil with a higher silt capacity would feel powdery like that, and they're not going to hold well together when wet. Clay is the smallest soil particles. Clay has a huge water holding capacity because of its large surface area, and clay soils are smooth and sticky when wet. So that's kind of how we tell the difference. And then really interesting, I like this picture you see here on the left. So you see sand, you get these, you can see these particle shapes, these kind of angular particle shapes. The silts, you can see really, really tiny particles. And then you see clay, though. These are really, really tiny particles, but they're these tiny platey shaped particles, which is how they have such a high surface area. And that's going to be an important difference with clay. So when we look at soil particle size, just another way to look at this, if we were to blow this way up, you got sand, think about what sand actually looks like when you see it, but it's blown up like this just to try and give us an idea of what silt and clay would look like, but we can't see silt or clay. It's just too small. Sand is the largest of the soil particle size. Clay is the smallest. Sand has high permeability, so water goes right through sand. Clay has the smallest permeability. Think about that plate structure and how it would be hard for water to go through that. And then think about also the idea of just once again going back to the beach, because it's kind of a simplistic way to think about it. But at the beach, your soils have a really high sand content. The water comes in on the shore. It comes in, hits the sand, and then just goes right through, because sand has a really high permeability to it. Whereas if our soils were clay, which is what you get at like a lake or a river, you got water sitting on top of it, and it sits there for a long, long time. And so, how do we separate our soils? Or now that we know that every single soil is a little bit of sand, silt, and clay, why does that matter, or how does that help us? And the big thing is that then we've come up with 12 main soil textures. There's more, but there's 12 main ones that most people refer to. And so when looking at the soil texture triangle, you'll see it's a triangle, so there's 3 big parts, which are going to be our 3 main components. So we got our clay part right here at the top. We've got our sand part over here on the left, and our silt right here on the right. And so you just have to make sure you read the chart correctly when you're going through it. So if I'm looking at my silt, it's right here. It goes from smallest silt level to largest amount of silt, right? Because if it's a very silty soil, it would be one that has a high silt component. My percent sand starts off here, so lowest percent sand to highest percent sand, because if it's got a lot of sand in it, we'd classify it just as a sand. And then the same thing with clay. No clay here to highest amount of clay. And so you can see the best soils. If we were just kind of generally speaking, the best soils, you'd be looking for about 10 to 20% of clay, and then equal amounts of sand and silt. So if I go to 10 or 20% of clay, which is right here, and then I start thinking about like equal parts of sand and silt, like a 50-50, I start getting into this area called loam. And then if you say to yourself, well, Dr. Arroyo, you said sand, silt, and clay. What's loam? Loam is kind of just the combination of all of them. Loam is that kind of middle point where you get the kind of the best of all worlds. Now, this is a good point when you have the lecture notes to hit pause, and especially because the way I'm recording right now, I have a link right here to a website where it talks about advantages and disadvantages of clay, sand, silt, and loam. So this is a good time to pause, take a look at that, and then we move on. All right, so here's some of those ideas that I'm talking about. I'm going to move myself over here right into this gentleman's hand. So what's important about texture, to me, they really focus on these ideas specifically: water holding capacity, drainage, aeration, organic matter content. So if we look at a pure clay soil, let's start here in this top right here. If we have a pure clay soil or a clay soil that's really high in clay, you got very small particles, so you got really high water holding capacity. You got low mobility of the water through the soils. You got low aeration because you have so much water taking up all the pore space. But what's interesting, because you have low mobility, is you have less water available to the plants due to that low mobility. So you have a lot of water in your soil, but it's not actually water that's going to go to the plants. So that's where mobility becomes important. And that's why when we talked earlier about silt, we said it's always good to have silt in your soil because it can hold water, but it holds water that is available to the plants. And so let's look at silt. If we had a soil that's more pure silt, also small particles, but if we're going to kind of go with the three the three components of soil, then we could kind of say medium particles, but they are pretty small particles. You got low to mid holding capacity, low to mid mobility, and you got less water available to plants due to low capacity and mobility. But you just said that that silt is good for holding water. It is. It's good for holding water. It's not the best at it. It's just you need silt in your soil to make that happen. So then let's go to loam. Let's go back up here to loam. A loam is a blend of the particle sizes. It's got high water holding capacity. It's got good water mobility, and it's got good storage and good availability to plants. And then if you say to yourself, okay, well, but that's more of what you were saying about silt. Well, look at where we classify things that would classify loam. How much of a percentage of silt is in things that would classify as a loam? And you're looking at stuff that's 40%, at least 30%, at least 30% silt. Up until 50%. So about quarter. Let's kind of ballpark it to like a quarter or a half of that loamy soil is silt, and that's that part of the combination is really good because that gets kind of the best part of the silt. The idea that silt really helps out in terms of that mobility of the water, the good mobility of the water, and good availability of the water to plants. And our last one, our sand. Really large particles, which means it's easy for water to go in and out between them because there's lots of space. So really low water holding capacity, high water mobility, but poor storage. Water comes in and water goes right back out. So it can move water all over the place. It just can't hold it at all. And so when you start looking at clay, which can't move water, but it can hold it really well, and you look at sand, which can't hold water, but it can move it really well, and then you look at silt, which is like it's almost in the middle, but it's not quite perfect. But then you combine silt and sand and clay in a nice combination of loam, and you get this beautiful blend of particle sizes, high water holding capacity, good water mobility, good storage, and good availability to plants, which is exactly what you're looking for, when you want to, plant crops or really grow something and have it stick. You want to have a nice easy soil to grow in, and one where it's very easy for the plants to get nutrients, very easy for the plants to get water, and they grow like there's no tomorrow. So let's look at that soil texture triangle. I think if I go back to the top here, I'll be out of the way. Let's see what we got here. So what is the soil texture of a soil comprised of? So let's if we did 30% clay, 30% silt, and 40% sand, where would we end up? So the answer is a clay loam. Oh, let me go back real quick. So let's walk through that. So 30% clay. So here's our clay. So we would kind of draw a line like this and say, okay, there's our line. So something's got to cross that line. 30% silt. So we're right here. So 30% clay and 30% silt gets us right there. And then if we look for 40% sand, we find that that's already there, because if you get two of these, you're going to end up at the third one. And that puts us right in this clay loam area. So hopefully that helps you in how to use a soil texture triangle. And if not, hey, guess what? We're going to do a bunch of that in lab. We're going to just kind of do this over and over again. But if we were to change it up, let's say we did 20% clay. So 20% clay would be this line here. And then if we did 20% clay and we still did 30% silt, so 20% clay and 30% silt would take us right here, and we go from instead of a clay loam, we just have a loam. We'd be right in that kind of middle kind of category, which means if we had 20% clay and 30% silt, We got to get to 100, right? So that means, what do we have left? 50% sand. It's always got to add up to 100. Kind of makes it easy. All right, our next topic in terms of soil physical properties, soil surface area. So the greater the surface area, the greater the ability to enter into chemical and physical reactions. Now, if you just quickly think back to some of the stuff I've already said, you should be sitting there going, clay, 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 because clay has a greater surface area than either sand or silt. So the surface of the soil particles offers a resistance to the flow of water. So the more surface that's in contact with the flowing water, the greater the resistance posed to the water. So that means low permeability. So the more surface in contact with flowing water, the greater the resistance posed to the water. So if we think about it, we said sand. Sand really lets water move right through it. Whereas clay doesn't let water move right through it, and that's permeability. How fast is that water going to be able to move or permeate through the soil? And so, if we compare the surface areas of the three textures, you got sand, silt, and clay. So 1 gram of sand would be in surface area would be equivalent to 3 lines on a page. So if we took a sand molecule and we cut it in whatever way we could to flatten it out as much as we could, it would cover like 3 lines on a page in your book. Whereas if we did the same thing for 1 gram of silt, it'd cover up about like 4 pages in your book. If we did the same thing for the plate-shaped soil clay that we have, it's equivalent to whatever house you live in, the surface area of all the walls, floors, and ceilings of a house. So huge amount of surface area. So I'll move myself down here. Now if you say to yourself, I don't understand, it doesn't make sense, the whole idea of surface area. Well, here, try and think about it this way. So clay particles have about 1,000 times as much external surface area as the particles in an equal weight of sand. So it's a huge amount more of external surface area than sand. The effect of decreasing particle size on surface area can be illustrated with a deck of cards. So right here, stacked together, this deck of cards only has 25 inches of surface area. But when you separate as individual cards, the deck has a surface area of nearly 1,000 square inches. As another example, consider a room in your home. Pack as many basketballs or golf balls or pinheads as possible. Then multiply the number of balls or pinheads by the surface area of each. You will find that the total surface area of the pinheads, so just the little tiny heads on a pin, is substantially greater than for the basketballs and golf balls. And if it's still hard for you to figure out, I would press pause right here and watch this cool video on surface to volume ratios, because I think that really kind of helped me out. Moving on. Alright, soil structure. Move myself in the middle here. Alright, structure is the arrangement of individual particles in relation to each other. So, so the idea of these, of all these soils, all these individual pieces of the soil then binding together, that's going to be our structure. And the small groups that they bind into are called aggregates. Aggregates are then going to bind with other aggregates to form either beds or clods. Beds is going to be the term that you hear most often. However, they're kind of the same and then kind of different in that soil beds are natural, relatively permanent aggregates which are separated from each other by voids or natural surfaces of weakness, whereas soil clods are artificial structure units formed at or near the surface by cultivation or frost action. So soil clods have had something else that has made them form, whereas the beds are the natural aggregation within the soil. And when we think about beds, we think about some specific shapes. We think about spherical, blocky, columnar, or platy. And what does that mean? Well, here we go. First, let's talk about the idea of good tilth. Your book mentions this term, and good tilth just means the optimum condition of structure. And so the big thing to really think about is clay and organic matter and the role they play, again, in structure, as aggregates can't be formed without clay, because once again, it's that huge surface area, it's that stickiness. Those are really important in binding things together. Then we talked about the idea of sand and silt being the skeleton, and it's almost like if you think about like a house, you put up the frame and you got this big wooden frame in there. And that's your sand and silt. Your sand and silt are the wooden frame of your house. But then all the drywall and all that stuff that you kind of put together and start piecing everything together in the house to really get everything else up, that's your clay and your organic matter that kind of keeps it all together. And then because we talked about this before, all soil is half minerals and organic matter, and then the other half is air and water. Well, where is that air and water? It's in these large pore spaces, or macropores, and in these small pore spaces, which are micropores. And we'll go into that a little more later. But let's get back to this idea of structure. So we've got our individual particles. Our particles become part of a PED. The PEDs stack together and form our structure. And so here's that idea I was talking about earlier about spherical shapes and blocky shapes and platy shapes and columnar shapes and single grain. So our aggregates, our soil is going to come together. It's going to aggregate together. It's going to bind onto each other. Thankfully, we've got some clay in there that kind of gets it to stick together, unless it doesn't, and that's the single grain stuff where the soil breaks up real easily. And then when it binds together, it's going to bind together in different shapes. So we got granular shape, which this thing says resembles cookie crumbs. So that's one way to think about it. You got blocky, irregular blocks. You got prismatic, so vertical columns of soil. You got columnar, which are also vertical columns of soil, but that have a salt cap at the top. You got the platy, which is similar to like that basic structure of the clay. And then you got single grained. So let's kind of take a look at what some of those look like differently. So move myself here so you can see. Here's our scale. That's about 1 inch, which, if you put your finger up to there, you're going, it's not 1 inch. Yeah, because I blew up the picture. But just think about that in comparison to what we're looking at here. So here is your granular style, that cookie crumb style of soil structure. You got your blocky little blocks, platy, so more of a flat soil structure. You got single grain here, which, your sandier soils that don't bind together well. You'll see that kind of look. And then there's this massive one. And we didn't talk about massive yet, but the idea of massive comes with soil compaction or a lot of wetness in your soils to where it kind of clods together. So we talked about that idea of clods where you have some other force acting on it that makes it come together. So massive is I don't want to say no structure, because it is a structure, but it's almost like a structure where things are just kind of jammed together, and you can kind of see that here. It doesn't have like one of these specific shapes. It just kind of forms together, sort of a thing. Here's another look at it. So I think if I'll move myself down here, I'll be out of your way in terms of all these pictures. So granular, the cookie crumb, that's where you get more spheroidal. So it's more spherical, so it looks like rounded, like a sphere. And here's another look at some cookie crumb type soil. You got your plate-like soil here, and you can get a nice look at that where it's kind of arranged in these flatter, kind of just flat plates that kind of stack onto each other. You got your block-like structure, which are going to be common in B horizons. The spheroidal stuff's common in 8 horizons. We'll get to horizons, which are just the different layers of the soil. But so kind of deeper in the soil is where you're going to kind of see block-like structures being more popular. And then we got subangular blocky, which is so it's just more rounded. It's a more rounded blocky look than the angular blocky. And then we've got prism-like as well. So we've got columnar and prismatic, where we got the flat tops or the rounded tops. So here's kind of a look at that, the rounded tops versus the more flat top look of soil. All right, move myself up here again. And moving on to soil composition. So when we talk about soil composition, I think the easiest way to think about soil composition is just going back to what we talked about, the idea of our perfect soil, or what I described to you is that soil is made up of 4 parts. In a perfect world, those 4 parts are 5% organic matter, 45% minerals, and then 50% is air and water. And if we're talking about the most perfect soil, because your book does that a couple times, a medium textured, well aggregated soil should contain about 50% pore space with equal amounts air and water. So, in our perfect world, our every piece of our soil is 45% minerals, 5% organic matter, 25% air, and 25% water. And so let's take a look at an example right here on the left of this reservoir sandstone. So here's an outcrop of reservoir sandstone. Close-up look at those sand grains. And then if we look at this reservoir sandstone through a microscope, here are our sand grains. So the same thing that we're looking at here, we're looking at the sand grains here. And then we've got these big pore spaces, which are filled with water right now. Those are macropores. And then we also have little smaller micropores as well. And so here's just another way to look at it if it was diagrammed. So you got the pore space. This would be a macropore here, and currently having water filling that macropore here. And you can see over here we've got white, so that's our air and that's our water, and we got a nice balance of air and water in this specific sandstone. Bulk density. So bulk density is the weight of a soil in a given volume. So it's a ratio of the weight of the soil, and usually the oven-dried weight of the soil to volume. Soils with a bulk density higher than 1.6 grams per centimeters cube tend to restrict root growth. So when we're talking about bulk density, this next part's kind of the key part, where it says bulk density increases with compaction and tends to increase with depth. So when we're talking about bulk density, we're really focused on the idea of, can roots grow, and do we have permeability? Can water and air and roots move through the soil, or is the soil kind of restrictive to that? And that's the idea with bulk density. And so bulk density is it's really important to know, because for when you figure out your bulk density, you'll find that good ag soil should be less than 1.4 grams per cubic centimeter. If you got a clay soil, or if it's a more sandier soil, 1.6 grams per cubic centimeter. But it's really important to know, because if you've got issues with compaction, or just you're not getting a lot of, you're having some sort of problems with your soil, it's one decently easy measurement to get that would be really important, because it really helps you understand what's going on in terms of the permeability of your soil. How are roots, air, and water moving through the soil? So here's our calculation of bulk density. It's you just have your weight of your soil over your volume of your soil. So in this example, it weighed 1.3 grams, and it was just 1 cubic centimeter, which means our bulk density is 1.33 grams per cubic centimeter, which would be great because we don't have a super dense soil. And so one of the things, if you think about it kind of in terms of opposites, is if we're measuring the density, the denser it is, the less space we're going to have for air and water to move through the soil. Which takes us right here to soil porosity. Man, that's nice how that works out. So in terms of soil porosity, we're really concerned about our macropores and our micropores, and wanting to make sure that we have a lot of macropore space and micropore space, so that air and soil and roots, right here talk about root penetration, and roots can get through. So here's some well-structured soil. We've got nice big aggregates of soil, but we also have room for air and water to move through the soil. Whereas here's an area that's suffering some compaction, where you can see we've got very small pores. We don't have a lot of big macropore space, so our water is kind of puddling up at the top here, and then maybe eventually leading to surface runoff. And we don't have a lot of good nutrient movement down through the soil. And bulk density usually does increase as you go down in the soil. I mean, it's kind of natural to think that just because of that weight from up top that it's going to be more compacted towards the bottom until, of course, we hit just bedrock. But we really would prefer this to have, because like we said, if we're living in an ideal world, our soil is half air and water. The only way you're going to have it be half air and water is if you've got these large pores for the water and the air to go in. What we just talked about earlier, thinking in opposites, porosity and bulk density are inversely related. So as porosity increases, bulk density will go down. As bulk density increases, porosity goes down. That's an inverse relationship. As one increases, the other one decreases. So here's another just look at a piece of soil and the idea of macropores and micropores. So a macropore here would be all this big open space right here, nice big macropore right here, same thing you're seeing right here. And then our micropores, we've got these little pieces of soil, and all those spaces in between little pieces of soil, those are our micropores, and we want to be able to use both. Both have roles to play. Usually when we're talking about the pores, it's usually water filling it up and then air taking whatever space is left. So once water vacates, or if there isn't any water, then air is going to try and take up those spaces. You can kind of see little holes and things like that, places where we could get roots to go through. And you can see, so if we're thinking about this as one big solid piece, but you can look at all those roots that made its way through. So there's macropores, and then you can see the little roots and stuff. That there's ways that water and air, and definitely right here you can see definitely the plant roots can work their way through the soil. Here's another way to look at it. So here's our aggregates. Our aggregates, kind of put together in our PED. There's all this other stuff going on, and eventually we'll, get to some of that stuff like our organisms and our bacteria and our fungi. But focusing on our porosity right now and our pore spaces. So you can see here's our macropores right here, where it's easy for water and air to move through. And right here, micropores within our aggregate here, as well as you can see air moving in, plant roots moving in, all sorts of stuff that we want. We want this stuff happening. We want water and air to be able to move in here, because then that gets water and air to our plant roots, which they need for survival, as well as water provides us our solution, gets us to our cation exchange, gets our plants the minerals that they need, and we start that wonderful connection that plants have with the soil, and it becomes this beautifully intricate web of wonder, for lack of a better term. And don't forget organic matter. We're going to spend a lot of time talking about organic matter because it's hugely important. Even though it's only 5% of the soil, it's hugely important. Soil swelling. So usually it's when you have a high clay content in your soil. You have expansive clays being a source of concern because they can shrink and swell according to their moisture content. And when you see kind of look like this, you got that clay content. We walked through the parking lot the other day, saw a similar thing going on. So you're either going to get swelling where you'll get a bump. So like this, you get this crack in this driveway where it's obvious that that things are pushing up from underneath. Whereas other places you can see shrinking to where you'll get depressions setting in. So it can be one or the other, or you can be in places where it's a kind of a constant upheaval of shrinking and swelling, which is even worse. At least if you had one, you kind of know what the issue is. But if you have both things happening, then things are going up and things are going down, and that just sucks. Why would it suck? Well, because we're really concerned with if we were doing construction. So if you're putting structures like houses or, in this case, the blacktop for the driveway, or highways and roads, things like that, you really don't want to have to. These things cost a lot of money and take a lot of time to fix, and so we don't want to really deal with those problems. So it's really it's a soil problem, but it's related to engineering and really not wanting to have to correct these sorts of things later on. But it just kind of depends. Not everywhere has these super high clays. It says right here, bentonite clay is a highly expansive clay, so that would be one. If you knew that was in your soil, you'd kind of want to avoid building there if you could. Soil strength. I know our chapter doesn't focus on this at all as a physical property, but I think it's important. When we say strength, we're talking about the soil response to mechanical forces, so any sort of forces that are put on the soil, and stickiness is a strength measurement, and that's the one that's really the only one that's important to agriculture. So it's very important to the idea of tillage or cultivation. So stickier soils can easily clog plows, cultivators, or even seeders. And then we said earlier, clay is kind of a plastic, sticky feeling when wet. So if you've got high clay content but low organic matter, that's where you're going to get this high stickiness, which is going to be harder to till up. If you've got enough of an organic matter component mixed in with a high clay content, then you won't get as much stickiness. And also, if you have more sand or silt in your soil, then you'll also have less stickiness. Soil temperature. So that's the only one of these physical properties that is constantly changing, unless, of course, you just happen to be in that perfect area where you're the shrink swell clay. But then again, it's the soil temperature that has a part to play in that shrinking and swelling. So soil stores heat and releases it when air is cooler, just kind of like water does as well. Same sort of thing. Soil is a great temperature buffer. Only the surface varies as much as the air. Once you get 2 to 3 feet deep in the soil, daily fluctuations no longer occur. What does that mean? So, if you get 2 to 3 feet in the soil, what happens during the day when it heats up or it cools off or any of that stuff? It doesn't happen. It just stays the same temperature 2 to 3 feet deep. There is no change. There is no, well, it's going to be cold this morning, then it's going to heat up in the afternoon, and then it'll cool off at night. Nope, same temperature all day long. If you get 20 feet deep, you don't even get a change in seasons. It doesn't matter if it's, snowing on the ground or it's 110 degrees outside. 20 feet deep in the soil, it's the same. It's the same all year around. And, how does that work? Well, it's just the idea of it being insulated. and it's just you don't have that effect. The daily fluctuations come from precipitation and temperature fluctuations, but you don't get any of that once you're deep enough into the soil. Wet soils are more of a buffer than dry soils because they have a greater heating capacity, because we talked about the idea of water does the same thing we talked about earlier, storing heat and releasing it when it's cooler. Evaporation cools wet soils as well. Soil temperatures can be modified in agricultural purposes. Mulch is probably the most common one that people know, even if we're talking forestry or horticulture or ag. People have seen mulch. And if you haven't seen mulch, then walk around campus and find any of the small trees or any of the beds, and you'll see tan bark or some sort of thing ringing around the trees, and that's mulch. It's put there to block sunlight and to also keep the heat from escaping, and it's really to sit there and aid whatever has been mulched. You also can you got contoured rows that'll do the same thing. So you get the beds contoured or shaped to face the sun so that they get more sunlight. So you can kind of change the soil temperature a little bit that way as well. So if we take a look at mulch specifically, so this study used a grass mulch at 4 tons per acre, and so you can see in terms of those daily fluctuations. At 12 a.m., 6 a.m., soil temperatures under 70. Then without mulch, by noon we get up to 85, give or take, and then we come back down and get back under 70. With mulch, you get much less of a fluctuation. So we're under 70, and then we barely just get above 70, and then we're back below 70. So much less fluctuation with that mulch, which is similar to what we said about if you kind of have layers of soil, or once you get deeper into the soil, because like we said, a couple feet into the soil and you don't get those daily fluctuations at all. So if you put 6 inches of mulch or whatever on top of there, you're gonna really decrease those daily fluctuations that the soil sees in terms of temperature. In terms of soil air, air is needed in the soil for the respiration of plant roots and the microorganisms within the soil as well. They need that air. It's weird to think about because you're like, no, it's under the ground, right? All the air is up above, but no, the air needs to go into the ground as well. And we've discussed that before with the idea of the pore space and air filling up the pore space not occupied by water. Usually, soil air is higher in carbon dioxide than surface air because the carbon dioxide builds up because of the respiration of the soil microbes. So all those little microorganisms, all those things in the soil, they're in there eating, doing all their sort of stuff, and that's creating CO2. So there's a creation of CO2 within the soil. So there's air coming in to the soil, but there's also air and the parts of air being created within the soil as well. You can have a lack of oxygen for healthy soil formation or plant growth due to things like flooding or high clay contents or soil compaction, which we've discussed before, or impermeable layers like hard pans, which we've previously discussed, the idea that you create almost like the little concrete layer there. So you get those sorts of things, and it really creates a lack of oxygen that we need penetrating through the soil to make it healthy for all those microbes and plant roots to be able to flourish within the soil. Sandy soils and well-aggregated soils have a large aeration capacity, and aeration capacity is just really what we're talking about is the amount of macro pore space. So your large pores. So when we're just saying you have a high aeration capacity, you have a high amount of large pore space, which we know sandy soils do because water comes in and just flows right through. And then well aggregated soils, that's if we had that perfect nice mixture. Here's a little piece, here's a little piece, here's a little piece, and we've got plenty of room for the water and the air to penetrate in, and the plant roots and whatever else we need. We've got plenty of macro pore space, so that makes sense to us. So here, in just talking about the idea of air and water within the soil again, so you can see here in a wet soil, you get most of the pore space. There's our aggregates. Most of the pore space being taken up by water, and then whatever was left is getting taken up by the air. Well, we got a dry soil down here. Instead, you get this thin film of water is tightly bound to the soil particles. We'll talk about that when we get to soil and water relations. And then the air is taking up all the rest of the space. So air is just kind of sitting there ready to take up whatever space the water doesn't occupy. And then our soil color. So soil color is a good indicator of other soil properties. So darker soils are usually higher in organic matter than surrounding soils. Red or orange soils indicate high oxidation of minerals and possibly low fertility. White layers are usually areas of salt accumulation. Blue, green, or gray indicates long periods of low oxygen, like in the bottom of lakes, or areas where we suffer from compaction or hard pan, or areas under hard pans, things like that, where stuff's not able to go through the soil really well. And if you have rust-colored nodules, that means shorter periods of low oxygen, like in ephemeral lakes or flood basins. So not quite the blue, green, or gray. You get a rust-colored instead, means that there were little bouts of low oxygen, but then they managed through it. Whereas the blue, green, or gray, there was long periods of low oxygen, and you don't have that as healthy-looking soil. You got much lighter colored soil. How do we figure something like that out? Well, it's something we're going to definitely do in lab. I'm going to move myself down here. We're going to do the Munsell color charts, where you can kind of see here, you get a piece of soil, and there's all these different hues and chromas, and we're going to figure out which is the one that it looks closest to, and that's going to help us figure out what kind of soil that we had. So, fun little exercise that we'll do in lab this week. And so that's it in terms of soil physical properties. I'd love to say, are there any questions? But I know that's not really the case right now. But if you do have a question, just go ahead and email me and let me know.